Good everyone, my name is Graphics. In our previous video, we discussed about elements and we said element can either be passive or active. Now, in this video, we want to be talking about how elements are arranged in a circuit. Now, elements can be arranged either in series or in parallel. When the element is arranged in series, they are arranged on a straight line. We say they are in line, such that when the voltage source produces a current, the same current flows through each of those elements. Now the element here is a resistor, so I will say the same current flows through each of the resistor. It means that the voltage produces a current which I call my I subscript T, which is called I total. The total current produced by the voltage enters each of these resistors. So let's say that A is the starting point here. When it flows, I total will start from here, flows into here, I total will come out here. So the same current flows through each of these resistors. So in this case, we say this is what? A series connection. Now, and we say that in a series connection, the R total, which is called also the R equivalent, is equals to the sum of what? The resistors. The sum of what? Each resistors. Right? So if the resistor is more than one, you're going to add all of them. So this is the general formula for what? Resistors in series. Now, there's something about a series connection. The same current flows through the resistor, but different voltages across each resistor. So meaning that the voltage in resistor 1 is not the same voltage as resistor 2, neither is the same as resistor 3, as long as what? Each resistance of each resistor are different. That means if the resistance of this resistor is 2 ohms and the resistance of this resistor is 3 ohms, the voltage can never be the same. So the resistor must be different for the voltages to be what? Different. So this different voltage flow through a resistor. Now, in terms of parallel connection, when our voltage source produces a current, we call it I subscript T, which is called I total. The current flows here and get to this point here, this node, right? You get to this point here. Now what is happening? In a parallel connection, each resistor are parallel to each other, right? So when this current, and the reason is this, when this voltage source produces a current I total, when it gets to this point, it splits because of what? It wants to cover more ground. Just like when you are chasing somebody, right? You are two people chasing one person and you get to a junction and you can't find the person here. What will you do? You tell one of them to go to the left and another one to go to the right. Another one to go, and you yourself you go straight so that you'll be able to see you cover more ground. The same thing current acts in that manner. When the current gets to a point, right, it splits. So at this point here, I total I mean, it will give me the I1, right? Going through R1. At this point here, this will give me the I2 going through R2. At this point here, this will give me the I3 going through R3. You can say that. Now, different currents in the name of I1, I2, and I3 are flowing through different resistors in the name of R1, R2, and R3. So in this case, you see each of those resistors are in parallel. So we can easily say that my R total is equals to R1 parallel to what? R2 parallel to what? R3. This is how I write them. Now if I want to put it in my formula here, we are going to say that you multiply the three resistors R1, R2, and R3 all over. You take two at a time. First one is R1, R2, that's the first one, plus R1, R3, that is the second one, plus R2, R3. No one must repeat each other. R2, R3. You can see that? So we say this is what? My R total. This is the general formula for resistors in parallel when there are three. But what about if there are two of them, two resistors? So if it's two resistors that you have that in parallel, you say that your R total is equals to R1, R2 all over R1 plus what? R2. So these are resistors in parallel. Now, you might be wondering, you might be asking yourself, how do we come about this formula? By the end of this video, you need to stay tuned. By the end of the video, I'm going to prove on how I got about this and this. But before then, in a parallel connection, different current flows in each resistor, but the same voltage. It means that the voltage in R1 is the same as the voltage in R2, is the same as the voltage in R3, right? Now, unlike the series connection, which different voltage flow. So I mean that if it's 2 volts that is flowing through here, this will be 2 volts and this will be what? 2 volts. So in parallel connection, the voltage are the same. In series connection, the voltage are different. Now there's one advantage of a parallel connection. Let's assume if this resistor here is bad, it doesn't stop current from flowing through each of the remaining two resistors because they have their own node. For instance, if R1 is bad, it doesn't stop R2 from R3 from receiving current. If R2 is bad, it doesn't stop. If R1 and R2 is bad, it doesn't stop R3 from what? From receiving current. And this is how we connect our home appliances. That is why if our TV is bad, it doesn't stop our radio from working. Or if one bulb in our house will get burnt, it doesn't stop the rest bulb from what? From working. And the good news here is this. If the voltage here is 100, it means the voltage across each resistor is what? Is 100. But in this case, the disadvantage of this is this. If one of these resistors is bad, the rest resistor will not function. Right? Now, and again, in this place, in this series connection, the voltage is different. The more resistor you have, the higher the resistance and the lower the current. The higher the resistance, the lower the current. So if I continue increasing my resistors in series, the current being supplied will be what? Will be reducing. There will be a time that what? You will not even see any current dissipated in each of those resistors because the resistance is high. That is why if you take your normal car battery or your normal phone battery, the phone battery can put on your phone, but the battery of the phone cannot rotate your fan or put on your light bulb. Is that taken now? Because of what? The light bulb has more resistance than the battery can accommodate. Is that taken? So this is why we don't use series in our homes. We make use of what? Parallel. Because the parallel, no matter what, the current, the voltage across each of those resistors are the same. Now, like I said earlier, let me now prove on how I come about R total to be equal to this and R total to be equal to this. Now, let's move forward. Proof. In this case here, when the current, when the voltage source produces a current, right? We say that the same current flows through each resistors, correct? Now, but the voltage across each resistor are different. So it means that the voltage supply, right, is the addition of all the voltage drop of each resistors. What I mean is this: when I multiply R, we say that what is the voltage. Because, for instance, let's move forward. So I'll call this to be my equation what? Equation 1. Now from here, I can now say that recall, according to Ohm's law says that the voltage across a meter wire is directly proportional to what? To the current flowing through those wire, provided that what? The resistance of the wire are constant. So I'll call this V is equal to what? IR, and my R should be my R total, which I since I saying R equivalent, and my I is given as what? My I total. Right? In bracket, I'm going to put what? Ohm's law. Now, I'm going to substitute wherever I see V, and I'll call this to be my Vx. So, if I have Vx, it means I'll have I total, R total. So anywhere I see Vx, I'll put I total, R total. And anywhere I see V1, I'll put I1, R1. I see V2, I'll put I2, R2, and so on and so forth. So now in doing that, instead of me writing my V supply, my voltage supply, my voltage source, I'm going to say that my I total, right, R total, right, is equals to, instead of writing V1, I'm going to put I1, R1, right? Plus, instead of writing V2, I'm going to put I2, R2. Plus, so I'm writing V3, I'm going to put I3, R3. Is that taken? Because whenever current meets with resistance, there's always a voltage drop, and this is what we have here. Now, we said earlier that the current in a series connection are the same. So it means that the total current is the same as each of those currents that is associated with each resistor. So it means I total is the same as I1, I total is the same as I2, and I2, they are all the same. So I can choose to say that I can decide to say that the I total here, R total, or with R equivalent, is equals to, I can have to say I1 is saying I total R1 plus I2 is saying I total R2 plus I3 is saying I total R3. You can see that because the same current are the same. So if I can choose, I can even say everything is I1. I can easily say everything is I2. I can easily say everything is I3. Now if I should write this, my I total R total is equals to, what is common in this I total is common. So I will now be left with what? R1 plus R2 plus R3, right? Because I total times R1 will give me I total R1. I total times R2 will give me I total R2. I total times R3 will give me I total R3. Now, this will equate this, your normal algebra. So we left with what? My R total is equals to what? R1 plus R2 plus R3. So this is the general formula for resistance in what? Series. So if the more resistance, you just add plus dot 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 plus and so on and so forth. So I can plus dot 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 plus Rn. So we're having that. So we just proved this. So whenever you are told to calculate the total resistance of a circuit and you find out that the resistance or the resistors are in line, when I mean in line, they are arranged on a straight line. When I mean on a straight line means they are in series, you are going to sum the total, add everything all together. Now, in terms of parallel connection, now let's take that and see. We want to prove, just like we did for the other. If the voltage source provide a current, we'll call it I total, and the I total, like I said earlier, gets to this point, this node, the current splits to cover more grounds. I1 will go this way to R1, I2 will go to R2, I3 will go to R3. And you might be wondering that must it be I1 that must go through R1, or must it be I2 that must go? It can. Why I'm taking I1 to go through R1 to reduce your confusion. If I like, I can put I2 R2. I can put I2 R1. If I like, I can put I3 R1. But then to make things more complicated. So to enhance your understanding, I'm taking 1 for 1, 2 for 2, and what? 3 for 3. Is that taken? Now, when this total current flows to cover more ground, it means that if they're entering into point A, right, they're going to come and meet at what? Point B. So it means that as I1 is coming here, I1 will be going back to this point. They'll meet at this point. So this also will be what? I1. As I3 is coming this one, it will come here and flow, and this will be what? I3. Then this is still my what? I2. So they are meeting at this point. So it means that what will now be here when they meet will be what? My I total. So when the three of them meet, because initially it was I total that split into I1, I2, and I3. So when they meet at this point, they will meet to become I total. So it means that my I total is equals to what? I1 plus I2 plus I3. Right? So this is just telling you that different current makes the total current in a parallel connection. Now from here, I can now say that I total is equals to I1 plus I2 plus I3, right? But according to Ohm's law, we say V is equals to what? IR, right? But V is equals to what? IR, that is my what? my Ohm's law. Now, if you make I instead of the formula, what we have here is I. So my I will now give me V over what? Over R. So this I is my I total, and this V is my voltage supply, and this R is my what? My R total. So I will say this is my equation 1 here. So I'm going to substitute this value into equation 1 above. So anywhere I see I total, I'm going to have um, V supply, the voltage supply or the voltage source, over the R total equals to, since it's I1, it will be what? V1 over what? R1 plus this I2 will be having V2 over what? R2 plus this is I3 give us what? V3 over what? R3. Now from here, as we're moving forward here, if you look at this, we said earlier that the voltage in a parallel network is the same. So I can easily say that the voltage supply here is equals to the voltage supply at resistor 1 because the voltage at resistor 1 plus is equals to what? The voltage at resistor 2 plus equals to what? The voltage at what? Resistor 3. So from here, it means that they are all the same. So I can rewrite this by saying that the voltage supply over R total is equals to the voltage supply over R1 plus the voltage supply over what? R2 plus the voltage supply over what? R3. If you remember what I said earlier on this video, I said that if this is 100 volts, it means 100 volts will be flowing across each resistor. So in this case, it means that the voltage supply at each of this resistor is the same. So I'm using Vs. If I like, I can use V1, V1, V1. If I like, I can use V2, 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 and everything should be V2. Now, what is common here? I can say that I can bring out my Vx, right? So I'll say that the Vs into bracket 1 over what? R total. You see that? Because Vs times 1 gives you Vs over R total. And this will give me, everything is common, I can bring it out to be what? Vx. Open my bracket, and I'm going to be having 1 over R1 plus 1 over R2 plus 1 over R3. How? Vs times 1 over R1 will give you Vs over R1. Vs times 1 will give you Vs over R2. Vs times will give you what? Vs over R3. So I only factorized here. Now, since I have Vs here and I have Vs here, it means Vs will equate Vx. So from here, I can easily say that I'm left with my 1 over R total is equals to 1 over R1 plus 1 over R2 plus 1 over R3. Now in this case here, I'm going to be looking for the LCM. Now finding the LCM here, the LCM here is R1, R2, and R3. So I write it out. R1, R2, and R3. Right? Now I'm still left with my 1 over what? R total here. So R1 in R1 is remaining R2, R3. So R2, R3 times 1 will give us R2, R3. Plus R2 in this means R2 in R2 is remaining R1, R3. R1, R3 times 1 will give me what? R1, R3. Plus R3 in R3 is remaining R1, R2. R1, R2 times 1 will give me what? My R1, R2. Now, some people, or you say, you cross multiply by taking this to this point and taking it to this point, right? But what I would just simply do is that what? If I invert the left hand side, I must invert the right hand side. So if I say that RO total over 1, I will surely have RO1, RO2, RO3 all over RO2, RO3 plus RO1, RO3 plus RO1, RO2, right? I will know anything over 1 will give you that thing. So we'll now be having my RO total is equals to RO1, RO2, RO3 all over RO2, RO3 plus RO1, RO3 plus RO1, RO2. So this is what we're having, and we've proved this here. So if you found this video helpful, please don't forget to click on the subscribe button. Thanks for watching.